Ever wondered how your phone predicts the next word you're going to type? Or how Google translates entire web pages in a blink? The secret lies in recurrent neural networks. Recurrent neural networks, or RNNs, are a fascinating subset of artificial intelligence that have a significant impact in our daily life. They are the backbone of many real-world applications, from language translation to stock prediction to speech recognition. But what sets RNNs apart from other types of neural networks is their unique ability to process sequential data. Picture RNNs as memory banks. They remember previous inputs by storing them in hidden layers and use this stored information to influence future predictions. This allows them to make sense of data where order matters, like sentences in a paragraph or stock prices over time. So RNNs aren't just networks, they're time travelers, making sense of the past to predict the future. With a basic understanding of what recurrent neural networks are and their importance, it's time to dive into the code. RNNs may sound complex, but building one isn't as daunting as you might think. To start, we'll need to import the necessary libraries. The libraries we'll need to import are NumPy, Keras, and Sclern, each with its unique role in the process. Let's start with NumPy. NumPy is fundamental for scientific computing in Python. It's particularly useful for handling large, multi-dimensional arrays and matrices of numeric data, which is crucial when working with neural networks. It also has a large collection of mathematical functions to operate on these arrays. Next, we have Keras. It's a high-level neural networks API written in Python and capable of running on top of TensorFlow, CNTK, or Theano. It allows for easy and fast prototyping and supports both convolutional networks and recurrent networks, as well as combinations of the two. With Keras, we can build our RNN model in a more simplified and efficient way. Lastly, we have Sclern, or more officially known as scikit-learn. This library is built upon NumPy and SciPy, providing a selection of efficient tools for machine learning and statistical modeling. It includes several algorithms and utilities, including support vector machines, random forests, gradient boosting, k-means, and dbScan. For our case, we'll use Sclern for scaling our data. Scaling is important in machine learning algorithms that calculate distances between data. If not scaled, features with high magnitudes can weigh in a lot more in the distance calculations than features with low magnitudes. The code for importing these libraries is typically straightforward. You use the import statement followed by the library name. For instance, import NumPy as NP, from keras.models, import sequential, and from sclern.preprocessing, import min-max scalar. Next, we'll create the dataset for our model. This is a critical step as the quality and type of data used can significantly impact our model's performance. In the next part of the video, we'll delve deeper into this. Now that we've set the groundwork, we're ready to build our recurrent neural network. Building the RNN involves a few steps. First, we initialize the model, then add the input layer and hidden layer. Let's dive into the details. Initializing the model is the first step in building our recurrent neural network. In Python, we use the sequential function from the Keras library. This function allows us to create a linear stack of layers in our model, which we can then populate with our input, hidden, and output layers. The code is straightforward. Model equals sequential, where model is the name of our recurrent neural network. Next, we add the input layer to our model. This is where our data enters the network. We use the add function combined with the dense function to accomplish this. Dense creates a densely connected layer. The code might look something like this. Model.add dense units equals n, input dim equals m, where n is the number of neurons in the layer, and m is the dimension of the input data. Following the input layer, we add the hidden layer. This is where the recurrent part of recurrent neural networks comes into play. The hidden layer has connections that loop back into itself, allowing it to process sequences of data over time. Again, we use the add function to add this layer to our model. Our model is taking shape. Next, we'll add the output layer and compile our model. The final steps in building the RNN are to add the output layer and compile the model. The output layer is added using the add function coupled with dense. It's here we define the final output dimensions. Compiling the model is done with the compile function, where we specify the optimizer and loss function. Choosing the correct ones is crucial for your model's performance. By now, you should have a clear understanding of how to code a recurrent neural network. Remember, the power of RNNs lies in their ability to remember previous inputs, making them ideal for processing sequential data. Happy coding!